We have seen in the last video base units and derived units. Now today we are going to see significant figures. The discussion starts like this. Whenever you make a measurement, whenever you measure a physical quantity, there is always some kind of error in the measurement. You have to deal with errors. You can never get exact measurement. One reason is that any kind of device you use to measure some quantity has its limitations. So that will prevent you from having exact measurement. There is a more fundamental reason also. The very nature of our reality prevents exact measurement of anything, and it comes from quantum mechanics. We are not going to discuss that right now. Okay, we just simply take the view that because of how complicated, how unimaginably complicated nature is, that we cannot make exact measurement. Alright. Which means that any measurement, which of course has two parts, we already know, the numerical part will contain errors. Say, someone measures the time period of a pendulum and gets this value 1.62 second, or someone measures the length of some object using some kind of device, say a ruler or something else, and gets this value 287.5 centimeters. None of these measurements is exact. Okay, they contain errors. Now we are going to discuss about that, but before that, let us mention the fact that these digits that you see in the numerical part of your measurement, 1, 6, 2, in the second one 2, 8, 7, 5, these are called significant figures or significant digits. But what is the significance of this term, significant figures or significant digits? Why should we give these digits this name? Let us now see how errors actually arise in a measurement. Say, I want to measure the length of this block of some material. What do I do? The simplest thing to do is to measure it using a ruler. So I place the block here and I place the ruler parallel to the block in such a way that I try my best to match these two edges. One end of the object or block I have tried to match with the 0 mark of the ruler, and then we can view the length of the ruler as gradually increasing as we move from the left to the right. It's a very strange way of looking at the length. I mean, length of course is not changing, length is fixed, but still, say we are looking at the ruler getting longer and longer as we look at the ruler from this point and we move rightward. So it gains more and more length, and in doing so we also keep track of which of these marks are surpassed during the journey. So during our journey at one point 1 centimeter mark is surpassed. That tells us that the object has length more than 1 centimeter. Eventually the 4 centimeter mark is also surpassed. So the object has length more than 4 centimeter. But we can clearly see that the 5 centimeter mark will not be surpassed because the object does not have that much length. But between 4 centimeter and 5 centimeter, what is the length actually? To know that, we then look at the finer lines. the smaller lines. You know that 1 centimeter can be divided into 10 equal parts. Each part is 1 millimeter. And our ruler can measure the length of 1 millimeter. So after looking at the smaller lines, smaller marks, we see that this last small mark actually has been surpassed. So the right end of the object lies between this last mark and the 5 centimeter mark. That tells me that the length of the object is 4.9 something centimeter. Note that these digits 4 and 9 that come from this device are exact. Okay, they are certain digits. They are known and they are reliable. So these digits are certain and reliable. However, next I want to put some other number here, and this is where I guess. And why do I do so? Because I have reached the limit of how small a length this ruler can measure. It can measure the smallest length of 1 millimeter, not smaller than that. That is the limit of this device. Okay. So the next digit or whatever digits I may come up with from my imagination after this will not be certain. These will be uncertain or unreliable digits. This 1 and 2. I may actually include more digits. However, the more digits I include, the less I can justify myself. Actually, I cannot also justify this 1, but for some reason, I feel that it should be 1. You won't necessarily feel that. You may feel that this should be 9.5. So here it becomes subjective. Unlike this 4 and 9, the other part becomes subjective. It depends on whoever is doing the measurement, making the measurement. What do we do here? Do we write 1 and 2, or do we write 5, or I may include 10 digits here? What should I do? You see, we actually know one thing. One thing is for sure, we have to write 4 and 9. Also, we cannot just not write anything after that, because we know it's not exactly 4.9, it's a little more than that. So we do a trade-off. What we do is we keep only one uncertain digit and do not write anything else after that. So we write the certain digits, that is the reliable digits, and one uncertain digit to kind of guess what the length should be. So that is the source of error. It comes from the limitation of this measuring device. That means my record of this length of the object should be this. Now, according to this rule of keeping only one uncertain digit, anything that you see, any kind of record of a measurement that you see like this, which has a number and followed by a unit, you know that the last digit is uncertain. The ones that come before that are certain. They have come from the device reliably. Exactly similarly, here 1 and 6 are certain digits which have come from some timekeeping device which was used to measure the period of that single pendulum. 2, however, has come from some human. So that is uncertain. Here also 2, 8 and 7 are certain or reliable digits. 5 is uncertain. This 0.5 has come from some kind of guesswork, like how we guessed 1 here. Okay. All starting as well as that uncertain digit, all of them are called significant figures or significant digits. Okay, so that's what they are. Now you may have already noticed one thing. It does not really matter where the decimal point lies. Okay, so that is one observation, because here the reading is 1.62, here it is 287.5. One more thing that is important is the number of significant figures. There are 3 significant figures here, 2 starting, 1 uncertain. This one has 4 significant figures, 3 starting, 1 uncertain. No problem, it's simple enough, but now a great confusion will come. Okay. This simple-minded approach of calling these things significant figures and keeping one uncertain digit will now confuse you like this. In all these things, we have really not put any attention to the unit, centimeter. That is, originally when we made the measurement, it must have been made in some unit, centimeter here, second here. But what if I change unit? Then what will happen to the number of significant figures? Let's see. Let me wrap this part and let me actually write what is there in the book so that you can go back and follow. Say, like this object, some other object has length, it's a long object, and its length was found to have this value, 2.308 centimeter. So you know again that there are 4 significant figures. Among them, 2, 3 and 0 are certain digits, and this 8 is uncertain digit. Now say we change this to meter. If we convert this to meter, what should we do? We have to divide by 100, and that will give us 0.02308 meter. Now what do you see? According to that same simple-minded rule, are we now having 1, 2, 3, 4, 5, 6 significant digits, out of which 8 is unreliable and the remaining ones are reliable? So it seems that the number of significant figures or significant digits depends on the unit we choose to make the measurement, or even when the measurement was made in one unit, as soon as you change it into another unit, the number of significant digits changes. Well, you may say, okay, so what's the problem? There is a problem, because the significant did you see that measurement? I wrapped it off. What does this actually tell you about this device? It tells you that your device can measure any integer centimeter length accurately. So it has given you 4. It is also able to measure 1/10 of a centimeter accurately. and accurately it gave you 9. And how do we know that 9 is accurate? Because only according to our rule, the last digit is uncertain, the ones before them are certain. This last one, however, is not accurate, means it's our guess. So that tells you the limitation of the measuring device, and that also tells you the precision of your measurement. Now, if simply by changing unit the number of significant figures changes, then I have lost this information, no? Naturally, because now I cannot really say what went on during the measurement of the length using this unit when I changed to meter. You can change it even more. Say you want to change centimeter to millimeter. To do that, you multiply by 10. So that gives you. Here, however, we still have 4 digits. Or you can go to micrometer also, micron. For that, you have to divide this by 1000. Multiply by 1000, because it's the smaller unit. So you get this value. As you go to smaller and smaller unit from meter, let's just talk about length. After meter, the next small one is decimeter, right? So to do that, to make the conversion, you multiply by 10. After decimeter, you have centimeter. You multiply by another 10. So you have to multiply by 100. After centimeter comes millimeter. To get to that, you have to multiply by another 10. That means to come from meter to millimeter, you are multiplying by 1000. After millimeter, these other much smaller units come. So after meter, deci, centi, milli, micro, nano, pico, femto, to go to those things, you have to multiply each time by 1000 instead of by 10. You already know these things, but again, more than reminding you, I am reminding myself. Here again, it seems like we have lost track of the significant digits. There seems to now be 5. So according to that rule, should I now consider 0 as the unreliable digit and these 4 digits that come before them as reliable? Obviously, I should not do this. So there is a problem. To get rid of this problem, we can make several rules for tracking the original significant digits when we change the unit. Let's see those rules. So it's like we are doing some fixes. We have done something and things went wrong the moment we changed units. So now we became cautious. No, we cannot call just about every digit significant digit. There should be some rule for recognizing this 2, 3, 0 and 8. So these are the rules. All non-zero digits are significant. Let me write SIG. This seems like a reasonable rule to make. Why? Well, because we are working with SI units, the factors by which we have to multiply to change from one unit to another are all powers of 10. So either you multiply by a power of 10 or divide by a power of 10. The result of that won't really give you any non-zero digits. So you see that only either you will have extra zeros you may have a decimal point, or I mean the zeros only change. That is why it seems reasonable to make this rule that all non-zero digits are significant. So by that rule we know that okay, at least 2, 3 and 8 are significant. They were significant initially, now also they are significant even after changing units. The question of being reliable and unreliable, that is still there. So this is one reasonable rule. Another rule, all the zeros between two non-zero significant digits are significant. If you have a zero between two non-zero significant digits, so we are talking about this zero, it should also be significant. So that way we can save this zero from being insignificant. So we have identified this zero also as significant. But the other units sometimes seem to have brought extra zeros. Those extra zeros should not be significant. Okay. So we further make this rule: if the number is less than 1, then any zero between the decimal, I have to wrap this, this of course there is no need for this anymore. Between the decimal point and the first non-zero digit is not significant, is non-significant. So in this part, let me read again. If the number is less than 1, which is the case here with this unit meter, the number is less than 1. So any zero between the decimal point and the first non-zero digit should not be significant. So this zero should not be significant. Okay, so that is another rule. Fine. But you can already kind of see that these rules are a desperate attempt to save a sinking ship. The ship will sink anyway, no matter what we do, wherever we put a board or what fixes we do. Let's see how far we can go. Then yet there is another rule. This rule says that the terminal or trailing zeros in a number without decimal points are not significant. Say your number does not have a decimal point, like this last one in the unit micrometer or micron, 23,080. Trailing zero or terminal zero means the zero that comes at the end of the number, those zeros. In this case, there is only one such zero. that is not significant. Okay, and this will soon cause further confusions. But anyway, there is one more rule. Let's see that also. The trailing zeros in a number with decimal point are significant, which we do not exactly see here. So let me show you the examples that the authors have written here. Say there is a length of 123 centimeter. If you change this to 123 meter. If we change this to centimeter, you have to multiply by 100. Okay. Now then, this is not what I wanted to show you. No, it's not this story. It's this other thing. Yeah, in these numbers, with whatever units there are after these numbers, say, actually I can write anything, but let me simply write this. In these numbers, these zeros are significant because these are numbers with decimal points. So these are significant. The non-zero digits are significant, but this one is not significant by that rule. Already you have got confused and you are thinking how many of these rules you have to remember. Luckily, you do not have to remember anything, because all these fixes cannot save us from this next confusion. And that confusion is this. Say someone has this record of some length of 4.700 meter. According to this last rule, this 00 should be significant. Oh, by the way, why do we make this rule? See, we make this rule to say what the accuracy of that measuring device is. It tells you that whatever measuring device has been used to measure this length of whatever object can accurately measure 1 meter, 1/10 of a meter, 1/100th of a meter, and actually 1,000th of a meter as well, but it cannot go beyond that. That is why this extra zeros. Okay, so here there are 4 significant digits, 4, 7, 0 and 0. But if you change this to millimeter by multiplying by 1000, so then what will you get? 4700 millimeter. Do you see the problem? This is a number with no decimal point. So according to this rule, the trailing zeros should not be significant. But if so, then the number of significant figures has gone down. From 4, it has gone down to 2, and we do not want that. So what can we do? In spite of having this many rules, we still cannot save this situation. It seems like the number of significant figures depends heavily on the unit. It should not be so, because otherwise we will only keep getting more and more confused. And the only way of saving us from this endless confusion is to use the scientific notation. In the scientific notation, what we do, we express the number in this form: a times 10 to the power b, where a is a number between 1 and 10. Actually, if a is less than or equal to 5, we may round off a to 1, or if a is greater than 5, in that case we may round a off to 10. But when expressed in this form, then we are expressing the number, the numerical part, okay, not the unit, in scientific notation. And in this notation, we say there are some other terminology also associated with this notation. Which are these. This exponent b has a name. It is called the order of magnitude of the measurement. And we say that the measurement is of the order 10 to the power b. What this tells you is a rough estimate of what the actual measurement is. Instead of saying what a is, we just simply estimate the number a times 10 to the power b with 10 to the power b. And when we do so, this is the language that we use, that the measurement is of the order of 10 to the power b, and where the order of magnitude of the measurement is only that exponent b. For example, the authors give example also. Say the diameter of Earth is 1.28, sorry, I don't want to be wrong, 1.28 times 10 to the power 7 meter. And from this measurement, you can say that the diameter of Earth is of the order of 10 to the power 7 meter, and it has the order of magnitude 7. As opposed to this, a very small object, say a hydrogen atom, has this diameter 1.06 times 10 to the power minus 10 meter. So to give a rough estimate of this diameter of a hydrogen atom, we say that it is of the order of 10 to the power minus 10 meter, or that its order of magnitude is minus 10. And to compare these two diameters, we say that the diameter of Earth is 17 magnitude more than the diameter of a hydrogen atom, because that is the difference between 7 and minus 10. Now, it's customary to make this part of the number, that is this a, have decimal point after one digit. Accordingly, this part gets adjusted with more 10 or less 10, you get the point. With this new thing, with this new rule that we have to use the scientific notation, that ambiguity is gone. Let's see how. You remember the source of the ambiguity. It arose because we were changing units. And in SI system, changing units means by multiplying by some power of 10. And that is the source of confusion. That's what changed our numbers so much that the significant digits got lost. Now that source of confusion has been kept separately in this part. So now if we change our unit, anything will happen in this part. This part which actually will have the significant digits will stay just like that. Let's see. Let's go back to that example of 4.700. What was the unit? Meter. And we know what this means. Here the significant digits are 4, 7, 0 and 0. Now if you want to change this to centimeter, you just write this. Still we have 4 significant figures. So do you see how this confusion is gone? Now if you want to change this to say millimeter, you multiply by another 10. Okay, so that's how this confusion is gone. If instead you want to change this to kilometer, say a higher unit, no problem. Instead of multiplying by a positive power of 10, you get a negative power of 10 and multiply by that. So in spite of changing units, that changing factor is separately kept. That is why the significant digits are not lost, and that is why we need scientific notation. Something else on these things. Yeah, the powers of 10, the authors say, are irrelevant in determining the number of significant digits or what the significant digits are. All digits in the base number are significant digits, and they continue to be so regardless of the unit. There is one more point that the authors make. If scientific notation is not adopted, we use those rules. However, I don't really understand why we have to not use scientific notation. Shall we not get back those confusions? I guess we will see as we go deeper in this subject, we will see how things are. Okay, I also don't know. We will see. And one more thing, say your number is less than 1, even in the scientific notation. You then customarily put 1 0 in front, right? Say something like this. Say 10 to the power minus whatever meters there. That 0 is not significant. Okay, it is never significant. That means in this measurement of the length of something, the significant digits are 1, 2 and 3. So the number of significant digits is 3. But of course, whatever zeros you are going to write after the decimal point, they are still significant. So in writing this part of the number, those rules still persist, they still work. And one more thing, in equations you are going to come across some exact numbers. They have infinitely many significant digits. For example, if you write the diameter of some circle or something like this, sorry, what am I writing? The radius of a circle is half of its diameter. Right, the circumference of a circle is 2 times pi times the diameter. In this type of relations or equations, you may measure diameter, radius, you may get a value of diameter, or you may measure diameter. So these are measured quantities because they are related to physical quantities. This number 2 is an exact mathematical number. Okay, so 2 is considered to have infinitely many significant digits. You can write 2 as 2 or 2.0, then this 0 will be significant. 2.00, as many zeros as you like to put, all of them will be significant. Why we will need these extra zeros? I think there are places where we will need to write extra zeros, even if the number is an integer after decimal point. Okay, so all of them will be significant, provided we are working with exact quantities. And for that matter, pi is also of that status. If you write pi in decimal form, 1592653, so whatever else other digits appear after this, all of them are significant. Okay, because the measurement of pi is not a physical measurement, it's a mathematically defined quantity. Do you see the difference? A physical quantity and a mathematical quantity are two different types of quantities. A physical quantity can be measured only using a device or instrument. Mathematical quantities are not measured like that. They are not measured, but they are defined using some rules or axioms. So that's all you have about significant figures in this book. After this, there are rules for doing arithmetic with significant figures or with numbers having significant figures. That we will do in the next video. So that will be all for today. So see you in the next physics video next week. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.